Right now, as you watch this, you are traveling through time at exactly 1 second per second. You cannot stop, you cannot slow down, you cannot reverse direction. You have been moving this way since the moment you were born, and you will continue until the moment you die. This feels so ordinary that you have never questioned it, but here is the strangest part. Physicists are no longer certain that time exists at all. The present moment you think you are experiencing already happened. By the time light from this screen reached your eyes, traveled down your optic nerve, and was processed by your visual cortex, roughly 80 milliseconds had passed. You are not watching the present. You are watching a reconstruction of the very recent past that your brain has assembled and labeled as now. You have never experienced the actual present moment, not once in your entire life. Your head ages faster than your feet. This is not philosophy. This is not metaphor. Atomic clocks placed at different heights show measurably different times. Over a 79-year lifetime, your brain ages approximately 90 billionths of a second more than your toes. The difference is tiny, but it is real. Time does not pass uniformly, even across your own body. At the center of a black hole, time stops completely. At the speed of light, time ceases to exist. At the quantum scale, time may be nothing more than an emergent illusion arising from deeper physics we do not yet understand. The future might already exist, fixed and unchangeable, waiting for your consciousness to arrive. Your sense that time flows might be the universe's greatest trick, a hallucination generated by a few pounds of wet tissue inside your skull. For 2,500 years, humans assumed time was simple. A river flowing forward, a clock ticking steadily. A universal metronome that the entire cosmos danced to simultaneously. Aristotle believed time was the measure of change. Newton believed time was absolute, flowing equally for all observers regardless of their motion or position. These ideas felt so obvious that no one seriously questioned them. Time was the stage on which the universe performed. The stage itself was fixed, eternal, unchanging. Then one patent clerk in Switzerland destroyed everything. In 1905, a 26-year-old named Albert Einstein was working at the Swiss Patent Office in Bern. He had failed to secure an academic position. His doctoral thesis had been rejected once. He spent his days evaluating patent applications for electromagnetic devices. He spent his evenings thinking about light. Every morning, he rode the tram to work, passing the famous Zeitglogge clock tower. He asked himself a simple question. What would that clock look like if the tram were traveling at the speed of light? The answer unraveled 2 centuries of physics. Einstein realized that if you traveled at light speed away from a clock, the light showing the clock's hands would never catch up to you. The clock would appear frozen, but your own watch would tick normally. The only way to make sense of this was to accept something radical. Time is not universal. Time is personal. Time passes differently for different observers depending on how they move through space. This was special relativity. It was just the beginning. 10 years later, Einstein completed general relativity and delivered an even more disturbing revelation. Gravity does not pull you down. Gravity bends time. Mass warps the fabric of space-time itself. Clocks run slower near massive objects. Time at the surface of the Earth passes more slowly than time in orbit. Near a neutron star, time crawls. At the event horizon of a black hole, time stops entirely relative to a distant observer. These are not theoretical curiosities. These are measured facts. In 1971, physicists flew atomic clocks around the world on commercial airplanes. When the planes landed, the clocks disagreed with identical clocks that had stayed on the ground. The airborne clocks had fallen behind by exactly the amount Einstein predicted. Every GPS satellite in orbit carries atomic clocks that tick faster than clocks on Earth's surface. Without correcting for this difference, your phone's location would drift by 10 kilometers per day. The technology in your pocket only works because engineers understood that time is relative. Everything you think you know about time is wrong. The present does not exist as a single universal moment. The past has not vanished. The future might already be real. The flow of time might be an illusion. Your memories, your plans, your entire sense of identity are built on assumptions about time that physics has systematically demolished over the past century. This is not abstract philosophy. This is the architecture of reality. You are embedded in time, warped by it, constructed by it. Every decision you make assumes time works a certain way. Every moment you experience is filtered through neural machinery that evolved to navigate time on the African savanna, not to comprehend time at the scale of black holes and light speed. Your intuitions are not just incomplete, they are fundamentally misleading. By the end of this journey, you will understand what Einstein understood. You will see why physicists suspect the future already exists. You will grasp why entropy creates the arrow of time. You will confront the possibility that free will is an illusion generated by how your brain processes temporal information. You will learn what happens to time at the edge of a black hole, at the quantum scale, and at the end of the universe itself. The dimension you have been living in your entire life is stranger than you ever imagined. And the journey to understanding it begins with the simplest question you can ask. What is now? Point at something across the room. Go ahead. Extend your finger and aim at an object several meters away. Watch your finger arrive at its destination. That moment of arrival, the instant you perceive your finger reaching its final position, already happened. The actual event occurred roughly 80 to 100 milliseconds before you experienced it. You are not watching reality. You are watching a delayed broadcast. This is not a limitation of attention. This is the fundamental architecture of perception. Light travels from the object to your retina. Photoreceptors convert light into electrical signals. Those signals travel down the optic nerve at approximately 100 meters per second. The visual cortex processes the raw data, identifies edges, colors, shapes, and motion. Higher brain regions integrate visual information with data from other senses. All of this takes time, measurable time, unavoidable time. Your brain does not show you the present. It shows you a sophisticated reconstruction of the very recent past that it has assembled, synchronized, and packaged into a coherent experience. The label on this package says now. The label is a lie. The problem goes deeper than visual delay. Different senses have different processing times. Vision takes about 80 milliseconds. Sound takes about 50 milliseconds. Touch takes about 20 milliseconds. If your brain showed you each sense as it arrived, your experience would be chaos. You would hear the crack of a baseball bat before you saw the swing. You would feel your finger touch a button after you heard the click. This does not happen because your brain is a time editor. It holds incoming information in a buffer, waits for slower signals to catch up, and then stitches everything together into a unified experience. Neuroscientists call this temporal binding. The result is a coherent present moment that feels seamless and instantaneous. But that moment never actually existed as a single instant. It is a construction, a useful fiction, a story your brain tells you about what just happened. The specious present is what philosophers call this constructed now. It is not a point, it is a window. Research suggests this window is approximately 2 to 3 seconds wide. Events within this window feel like they are happening now. Events outside it become either past or anticipated. The boundaries are not sharp. They blur and shift depending on attention, emotion, and context. But the window exists. The present is not a knife edge. It is a smear. Consider the flash lag effect. When a moving object passes a flash of light at the exact same position, subjects consistently report that the flash appeared behind the object. The flash and the object were physically aligned, but the brain, predicting the moving object's trajectory, extrapolates its position forward. The result is an illusion where simultaneous events appear to happen at different times. Your brain is not just reconstructing the past, it is predicting the future and blending the prediction into your experience of the present. You have never experienced the actual current moment. Every now you have ever felt was already history by the time you felt it. This is unsettling, but it is only the beginning. The problem with the present moment extends far beyond neuroscience. Einstein proved that now cannot exist across any distance, The concept of a universal present, a single moment that encompasses the entire universe simultaneously, is not just difficult to perceive, it is mathematically impossible. This is the relativity of simultaneity. Two events that appear simultaneous to one observer will appear to happen at different times to another observer, moving relative to the first. There is no fact of the matter about which events are truly simultaneous across space. It depends entirely on your motion. Imagine two lightning bolts strike opposite ends of a train platform at what you measure to be the exact same instant. You are standing in the middle of the platform. Light from both strikes reaches you simultaneously. For you, the events were simultaneous. But someone on a train passing through the station at high speed will disagree. They are moving toward one lightning strike and away from the other. Light from the front strike reaches them first. For them, the front strike happened before the rear strike. Neither of you is wrong. Neither of you is experiencing an illusion. Simultaneity itself is relative. At everyday speeds, this effect is unmeasurably tiny, but it scales with velocity and distance. Consider the Andromeda galaxy, 2.5 million light-years away. If you are standing still relative to Earth, there is some set of events on Andromeda that are happening now. If you start walking toward Andromeda at a few miles per hour, the events that qualify as now on Andromeda shift. They shift by days. If you walk away from Andromeda, the events shift in the other direction. Just by walking across a room, you change what is happening now in a distant galaxy by a measurable amount. This seems impossible, but it is not a matter of perception or measurement error. It is the structure of space-time itself. There is no cosmic clock synchronizing the universe. There is no absolute present moment spanning all of existence. When you ask what is happening right now on a planet 1,000 light-years away, the question has no answer. It depends on how you are moving. The death of Universal now has profound implications. Every science fiction story that shows events happening simultaneously across the galaxy is physically impossible. The phrase "at this very moment," somewhere in the universe, is meaningless. We are not just delayed in perceiving distant events. We are fundamentally disconnected from them in time. There is no objective present connecting us. This is not a failure of technology or perception. This is reality. The present moment you feel so certain about, the now that seems undeniably real, does not exist in any absolute sense. Your brain constructs a local present from delayed sensory signals. Physics forbids a universal present across space. The moment you call now is simultaneously a reconstruction of the past, an interpretation shaped by prediction, and a concept that cannot extend beyond your immediate location without becoming ambiguous to the point of meaninglessness. You have never been in contact with the true present. You have only ever experienced edited, delayed, constructed approximations that your brain labeled as real. And if the present is an illusion, what does that mean for the past and future? If now does not exist as a universal moment, how do we define before and after? Einstein's answer was as elegant as it was disturbing. Space and time are not separate entities. They are woven together into a single four-dimensional fabric called space-time. And in this fabric, the distinction between past, present, and future is not what you think. The year is 1905. A 26-year-old patent clerk sits at his desk in Bern, Switzerland, evaluating applications for electromagnetic devices. His name is Albert Einstein. He has a wife, a young son, and no prospects for an academic career. His doctoral thesis was rejected the previous year. The physics establishment does not know his name. But inside his mind, a revolution is taking shape. Einstein had been obsessed with a thought experiment since the age of 16. He imagined chasing a beam of light. What would you see if you could run alongside a light wave at the same speed? Classical physics said you would see a frozen electromagnetic wave, stationary in space, oscillating in place like a still photograph of an ocean wave. But Maxwell's equations, which govern electromagnetism, said this was impossible. Light cannot stand still. It must always move at exactly 299,792,458 meters per second. Always. For everyone. This contradiction haunted Einstein for a decade. The solution came to him in a flash of insight while talking with his friend Michele Besso. The conversation lasted hours. The next morning, Einstein greeted Besso with a single sentence: "Thank you, I have completely solved the problem." The solution required sacrificing something sacred. If the speed of light is truly constant for all observers, regardless of their motion, then something else must give. That something was time. Consider a simple scenario. You are standing on Earth, holding a flashlight. You turn it on. Light leaves the flashlight at 299,792,458 meters per second. Now imagine you are on a spaceship traveling at half the speed of light relative to Earth. You turn on the same flashlight. Common sense says the light should travel at 1.5 times light speed relative to Earth. Your speed plus the light speed. But this is not what happens. The light still travels at exactly 299,792,458 meters per second relative to both you and Earth. The speed of light does not add up the way ordinary speeds do. For this to be mathematically consistent, time itself must behave differently for different observers. When you move through space, you move through time more slowly. This is time dilation. It is not an illusion. It is not a trick of perception. It is the actual structure of reality. The faster you move through space, the slower you move through time. At 50% of light speed, time passes at about 87% of the normal rate. At 90% of light speed, time passes at 44%. At 99%, time passes at just 14%. At 99.999%, 1 year of your time equals 707 years for a stationary observer. The relationship is precise. The mathematics are exact. Time is not a constant river flowing at the same rate for everyone. Time is personal. This leads to the most famous thought experiment in physics, the twin paradox. Imagine two identical twins. One stays on Earth, the other boards a spacecraft and travels to a star 10 light-years away at 99% of light speed, then returns. From Earth's perspective, the round trip takes slightly more than 20 years. But for the traveling twin, only about 2.8 years have passed. When the spacecraft lands, the traveling twin has aged less than 3 years, while the Earth-bound twin has aged more than 20. They are no longer the same age. The traveling twin has jumped 17 years into the future. This is not metaphor. This is not theoretical. This is measured reality. In 1971, physicist Joseph Hafele and astronomer Richard Keating conducted an experiment that would have seemed like science fiction just decades earlier. They placed cesium atomic clocks on commercial airplanes and flew them around the world, some eastward and some westward. After the flights, they compared the airborne clocks with identical clocks that had remained on the ground. The clocks disagreed. The differences were tiny, measured in nanoseconds, but they matched Einstein's predictions exactly. Time had passed at different rates depending on motion. The global positioning system depends on this effect. GPS satellites orbit Earth at roughly 14,000 kilometers per hour. Their clocks tick faster than ground-based clocks by about 7 microseconds per day, due to their lower gravitational field, and slower by about 7 microseconds per day, due to their velocity. The net effect is that satellite clocks gain roughly 38 microseconds daily, compared to ground clocks. Without correcting for relativistic time dilation, GPS position calculations would drift by more than 10 kilometers per day. Your ability to navigate using your phone depends on Einstein being right about time. But velocity is not the only thing that affects time. Gravity does too. 10 years after special relativity, Einstein completed his masterwork. General relativity revealed that gravity is not a force pulling objects together. Gravity is the curvature of space-time caused by mass. Heavy objects warp the fabric of space and time around them, and this warping affects how time passes. Clocks run slower in stronger gravitational fields. Time at sea level passes more slowly than time on a mountaintop. The difference is small, roughly 1 microsecond per year for every kilometer of altitude. But it is real. It has been measured. Atomic clocks at different heights show different times. The core of the Earth sits in a stronger gravitational field than the surface. Over the 4.5 billion years since Earth formed, the core has aged approximately 2.5 years less than the surface. The center of our planet is measurably younger than the ground you stand on. Near more massive objects, the effects become dramatic. On the surface of a white dwarf star, time runs roughly 0.03% slower than far from the star. Near a neutron star, time might run at 70 or 80% of the normal rate. And at the edge of a black hole, where gravity becomes extreme beyond imagination, something extraordinary happens. Time stops. Not metaphorically, not poetically, mathematically, observationally, actually stops relative to a distant observer. And what happens when you fall past that boundary challenges everything you think you understand about the nature of time itself. Imagine falling toward a black hole, not a small one formed from a collapsed star, but a supermassive black hole like the one at the center of the Milky Way. This monster contains 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. Its gravitational field warps space-time so severely that light itself cannot escape. The boundary beyond which nothing returns is called the event horizon. You are falling toward it. From your perspective, nothing unusual happens at first. Space around you looks normal. Your watch ticks steadily. You do not feel yourself slowing down. As you approach the event horizon, you experience no wall, no barrier, no physical sensation of crossing a threshold. You simply fall through and continue falling. Your watch keeps ticking. Your heart keeps beating. From inside your reference frame, time flows normally. But someone watching you from a safe distance sees something entirely different. As you approach the event horizon, your movements appear to slow down. Your radio signals stretch into longer wavelengths. Your image reddens as light struggles to climb out of the gravitational well. At the event horizon itself, you appear to freeze. Your image dims, reddens further, and gradually fades. But it never crosses the horizon. To the outside observer, you remain forever frozen at the edge of the black hole, suspended in time, never quite falling in. Both experiences are equally real. Neither is an illusion. You cross the event horizon and continue falling. The outside observer never sees you cross. Time passes differently, in different reference frames, so dramatically that the two experiences cannot be reconciled into a single coherent narrative. Once inside the event horizon, time and space exchange roles in a way that defies human intuition. Outside a black hole, you can move freely in any spatial direction, but you can only move forward in time. Inside a black hole, this inverts. You can no longer move freely in space. All paths, all directions, all trajectories lead to the singularity at the center. But the singularity is not a place in space. It is a moment in time. It lies in your future, the way tomorrow lies in your future. Inevitable, inescapable. Asking how to avoid the singularity inside a black hole is like asking how to avoid next Tuesday. One physicist described it this way: the singularity is not something you fall toward, it is something that happens to you. Space and time have switched their mathematical properties. The dimension that was once time-like has become space-like. The dimension that was once space-like has become time-like. The geometry of existence itself has transformed into something our evolution never prepared us to understand. If you fell into a supermassive black hole and somehow survived the journey, you could watch the entire future of the outside universe play out above you. Stars would be born and die. Galaxies would merge and drift apart. Billions of years would pass in the cosmos. While hours passed for you, you would witness the end of stellar formation, the evaporation of black holes, perhaps the heat death of the universe itself, all compressed into a brief window of your personal time. Then you would reach the singularity, and physics as we understand it would cease to make predictions. Now consider the opposite extreme. Not gravity slowing time, but velocity accelerating it. As objects approach the speed of light, time dilation becomes absolute. At exactly light speed, time stops completely. This is not gradual. it is total. For a photon traveling at light speed, no time passes between emission and absorption, regardless of the distance traveled. A photon leaving a distant star travels what we measure as 1,000 light-years. From our perspective, the journey takes 1,000 years. From the photon's perspective, the journey is instantaneous. Emission and absorption are the same event. The photon does not experience the trip because there is no time in which to experience anything. The James Webb Space Telescope captures light from galaxies 13 billion light-years away. That light has been traveling for 13 billion years from our perspective. From the photon's perspective, no time has passed. The photon that left a galaxy 13 billion years ago and the photon hitting Webb's detector are in the photon's reference frame, experiencing the same moment. Light exists at the boundary where time has no meaning. It is eternal and instantaneous simultaneously. This is why nothing with mass can reach light speed. As you accelerate toward light speed, time dilation increases. Your mass effectively increases from an outside observer's perspective. Pushing you faster requires more and more energy. At 99% of light speed, a 1 kilogram object carries kinetic energy equivalent to roughly 10 megatons of TNT. At 99.9999%, the energy requirement increases by another factor of more than 20. At exactly light speed, the energy required becomes mathematically infinite. The speed of light is not a speed limit that the universe enforces through some cosmic traffic law. It is a consequence of the geometry of space-time. Going faster than light does not mean breaking a rule, it means asking for something that does not exist. It is like asking to go north of the North Pole. The question itself stops making sense. If you could somehow exceed light speed, time would not just stop, it would reverse. You would arrive before you left. Causality would break. Effects would precede causes. The equations describing your motion would produce imaginary numbers and infinite contradictions. The mathematics is not saying no. The mathematics is saying the question is meaningless. Time dilation at airplane speeds is measured in nanoseconds. Time dilation near massive objects becomes seconds, minutes, years. Time dilation at black hole event horizons approaches infinity. At exactly light speed, time vanishes entirely. These are not separate phenomena. They are all manifestations of the same underlying truth. Time is woven into the fabric of space-time. Pull on space by moving through it, and time stretches. Warp space with mass, and time bends. Push to the extremes, and time reveals itself as something far stranger and more malleable than any clock could suggest. But there is still one question that Einstein's equations do not answer. They describe how time can speed up, slow down, or stop. They do not explain why time moves in only one direction. They do not tell us why yesterday feels different from tomorrow. They do not reveal why eggs break but never unbreak. Why we remember the past but not the future. Why the universe seems to have an arrow pointing relentlessly forward. The answer to that question does not come from relativity. It comes from a different branch of physics entirely. It comes from a single number that has been increasing since the first instant of creation. A number that connects time to disorder, information to decay, and the flow of moments to the inevitable fate of all existence. Play any video backward, and you will recognize it instantly as wrong. A shattered wine glass leaps from the floor, fragments flying upward, reassembling into a perfect vessel on the table. Spilled coffee rises from the carpet, gathering into a stream that flows upward into an overturned mug. A diver emerges feet first from the water, rises through the air, and lands gracefully on the diving board. These scenes look absurd, they feel impossible. Your intuition screams that time does not work this way. But here is the puzzle that has haunted physicists for more than 150 years. Every fundamental equation in physics works equally well forward and backward in time. Newton's laws of motion are time-symmetric. Run them forward and a ball falls to the ground. Run them backward and a ball rises from the ground. Both solutions are mathematically valid. Einstein's equations of general relativity are time-symmetric. Quantum mechanics, at its most fundamental level, is time-symmetric. Electromagnetism is time-symmetric. The deepest laws governing reality do not care which direction time flows. They work perfectly in either direction. So why does the universe care so much? Why do eggs break but never unbreak? Why does ice melt in warm water, but warm water never spontaneously freezes while heating its surroundings? Why do we remember yesterday, but not tomorrow? Why does time feel like an arrow flying in one direction when the laws of physics are perfectly happy with arrows flying both ways? The answer is not found in the fundamental laws themselves. It is found in a single quantity that the universe has been relentlessly increasing since the first fraction of a second after the Big Bang. That quantity is entropy. Entropy is often described as disorder, but this definition is incomplete. More precisely, entropy measures the number of microscopic arrangements that produce the same macroscopic state. Consider a box of puzzle pieces. When the puzzle is assembled, there is essentially one arrangement that works. The pieces must be in specific positions. This is a low entropy state. When the puzzle is dumped into a pile, there are billions of possible arrangements of the scattered pieces. This is a high entropy state. The assembled puzzle is ordered. The scattered pile is disordered. But what matters is not the order itself. What matters is the number of ways to achieve each state. Now consider a glass of water with an ice cube floating in it. The ice cube is a low-entropy arrangement. Water molecules are locked in a crystalline lattice, each one in a specific position. As the ice melts, those molecules disperse into the liquid, free to move anywhere. The number of possible arrangements explodes, entropy increases. The ice melts because there are astronomically more ways for the molecules to be liquid than solid at room temperature. Here is the critical insight. There is nothing in physics preventing the reverse process. Nothing forbids water molecules from spontaneously arranging themselves into a crystal while releasing heat into the surrounding liquid. The fundamental laws permit it, but the probability is so vanishingly small that it would never happen in the entire lifetime of the universe. If you shuffle a deck of cards randomly, the odds of returning to the original factory order are 1 in 10 to the power of 68. That number is larger than the number of atoms in the observable universe. The odds of a broken wine glass spontaneously reassembling are not just unlikely. They are so improbable that waiting for it to happen would take longer than 10 to the power of 10 to the power of 100 years. The age of the universe is about 10 to the power of 10 years. These numbers are not in the same conceptual universe. Time's arrow is not a law, it is a probability so extreme that it masquerades as a law. The future is the direction of overwhelmingly higher probability. The past is the direction of overwhelmingly lower probability. We are not moving through time in any mystical sense. We are rolling downhill on a probability landscape so steep that rolling back up is effectively impossible. But this raises a deeper question. If entropy always increases toward the future, why was it ever low in the past? Why did the universe start in a state of extraordinarily low entropy? This is the past hypothesis. It is one of the deepest unsolved problems in physics. The Big Bang was not an explosion of chaos. It was a state of remarkable order. Matter was distributed almost perfectly uniformly. The entire observable universe was compressed into a region smaller than an atom, yet that compression was smooth, even, structured. As the universe expanded, gravity amplified tiny fluctuations into galaxies, stars, and planets. Entropy has been increasing ever since. But the starting point was a state so improbable, so finely arranged, that it demands explanation. Imagine finding a deck of cards in perfect order, with no one around to shuffle it. You would demand an explanation. The universe presents the same puzzle on a cosmic scale. Why did it start in a configuration that was overwhelmingly unlikely? Physics does not answer this question. The laws describe how entropy increases. They do not explain why it was low to begin with. Some physicists propose that our Big Bang was not the ultimate beginning. Perhaps it was a local fluctuation in a larger multiverse, a pocket of low entropy in an infinite sea of chaos. Others suggest that time's arrow itself emerges from quantum gravity effects we do not yet understand. The honest answer is that we do not know. What we do know is that entropy's increase is responsible for everything you experience as the passage of time. Your memories exist because remembering is an entropy-increasing process. Your brain encodes information about the past by creating physical changes in neurons, building new connections, strengthening existing synapses. These changes are irreversible under normal conditions. They can only happen in the direction of increasing entropy. You remember the past because the act of forming memories creates disorder. You cannot remember the future because forming memories of the future would require entropy to decrease. Causality itself depends on the entropy gradient. Causes precede effects because causes are lower entropy states that evolve into higher entropy effects. If entropy could decrease, effects could precede causes. The logical structure of reality would collapse. Thinking would become impossible. Identity would dissolve. The arrow of time is not something your consciousness passively observes. It is something your consciousness is made of. Without entropy increase, there would be no memory, no causality, no experience of moments flowing from past to future. The second law of thermodynamics is not just a statement about heat engines. It is the reason you exist as a being who experiences time at all. Shrink down past atoms, past protons and neutrons, past quarks. Keep shrinking until you reach the smallest meaningful scale physics can describe. At this level, roughly 10 to the negative 35 meters, you have reached the Planck length. Here, the smooth fabric of space-time begins to dissolve, and with it, time itself starts to lose meaning. Quantum mechanics is the physics of the very small. It governs atoms, electrons, photons, and all the particles that make up matter. At this scale, reality behaves nothing like the world you experience. Particles do not have definite positions until measured. They exist as probability clouds, smeared across space, occupying multiple locations simultaneously. They are not tiny billiard balls following precise trajectories. They are wave functions, mathematical descriptions of likelihood, collapsing into definite states only when something forces them to reveal themselves. Time enters quantum mechanics in a strange way. The Schrödinger equation describes how quantum states evolve. It is the master equation of quantum mechanics, predicting how probability distributions change from moment to moment. And it is perfectly reversible in time. Run it forward and you get valid physics. Run it backward and you get equally valid physics. At the quantum level, time has no preferred direction. But something clearly does happen that seems irreversible: measurement. When you measure a quantum system, its wave function collapses. Before measurement, an electron might be in a superposition of spin up and spin down. After measurement, it is definitely one or the other. This collapse appears instantaneous. It appears irreversible, and it appears to single out a specific moment as special, the moment when the measurement occurred. This is the measurement problem, and it has tormented physicists since the 1920s. When does measurement happen? What counts as a measurement? Does the wave function really collapse, or does it only appear to collapse from a particular perspective? If collapse is real, it seems to violate the time symmetry of quantum mechanics. If collapse is an illusion, what is really happening? There is no consensus answer. Different interpretations of quantum mechanics give different accounts. Some say collapse is a real physical process requiring new physics. Some say collapse never happens and all possible outcomes occur in branching parallel universes. Some say collapse is a consequence of information transfer between the quantum system and its environment. The mathematics works, the predictions are confirmed by experiment, but the meaning remains disputed. Time becomes even stranger when you consider the energy-time uncertainty principle. Most people know Heisenberg's uncertainty principle for position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. There is a similar relationship between energy and time. The more precisely you know when something happened, the less precisely you can know its energy. The more precisely you know the energy, the less precisely you can know the timing. At extremely short time scales, this uncertainty becomes profound. Below about 10 to the negative 43 seconds, the Planck time, the concept of when becomes fundamentally fuzzy. Events do not have precise timestamps. They have probability distributions in time, just as particles have probability distributions in space. The question, "What time did this happen?" loses its sharp meaning. The Planck time is unimaginably brief. It is how long light takes to travel one Planck length. In 1 second, there are more Planck times than there have been seconds since the Big Bang. At this scale, our theories stop making reliable predictions. We do not know if time is continuous, flowing smoothly through every instant, or discrete, jumping in tiny quantum steps. We do not even know if the question makes sense. Now consider what happens when physicists try to combine quantum mechanics with general relativity. Both theories are spectacularly successful in their domains. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and forces at microscopic scales. But when you try to merge them into a single theory of quantum gravity, something breaks. The Wheeler-DeWitt equation is the closest thing physicists have to a quantum equation for the entire universe. It attempts to describe the quantum state of space-time itself, treating the whole cosmos as a single quantum system. And it contains a stunning feature. There is no time variable. The equation describes a static, timeless quantum state. The universe, according to this equation, simply exists. It does not evolve. It does not change. Time is not a parameter that the equation tracks. Time is absent. John Wheeler, one of the equation's creators, called this the problem of time. It suggests that if you could somehow view the universe from outside, you would not see it changing. You would not see events unfolding. You would see a frozen, eternal, four-dimensional structure. Time would not be a fundamental feature of reality. It would be something that observers inside the universe experience, an emergent phenomenon arising from the quantum state rather than a basic ingredient of existence. This idea is radical, but not arbitrary. It emerges directly from attempting to apply quantum mechanics to gravity, and it aligns with suggestions from other approaches to quantum gravity, including string theory and loop quantum gravity. Many theoretical physicists now suspect that time, at the deepest level, does not exist. What we experience as the flow of moments may be a consequence of how quantum information is organized, not a fundamental property of reality. Some interpretations of quantum mechanics push even further. They suggest that the future can influence the past. This is called retrocausality. The delayed choice quantum eraser experiment demonstrates results that seem to depend on measurements made after the particles were detected. It is as if the choice of future measurement reaches back to affect what happened earlier. This does not allow sending messages backward in time. No information travels to the past. No paradoxes arise. But it suggests that the quantum world does not respect the neat ordering of before and after that we take for granted. The past may not be as fixed as we assume. At quantum scales, it might remain undetermined until later events settle it. At the deepest level, physics can currently probe. Time dissolves into uncertainty, probability, and equations that do not require it at all. The ticking clock, the flowing moment, the clear distinction between past and future, these may be features of our macroscopic experience rather than features of fundamental reality. And if time is not fundamental, if it emerges from something deeper, then the question of what time is becomes even more profound. It becomes a question about what kind of structure could give rise to the illusion of moments passing. It becomes a question about the relationship between physics, information, and consciousness. In March 1955, Albert Einstein's lifelong friend Michele Besso died in Geneva. Einstein, living in Princeton and growing frail himself, wrote a letter of condolence to Besso's family. The letter contained a remarkable passage. "Now he has departed from this strange world a little ahead of me. That means nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." 3 weeks later, Einstein was dead. These were not the sentimental words of a grieving friend. They were not poetic comfort offered to ease the pain of loss. They were a precise statement of what Einstein believed his own equations revealed about the nature of time. The distinction between past, present, and future is an illusion, not a metaphorical illusion, not a spiritual illusion. A physical illusion built into the structure of the universe itself. This is the block universe, and it might be the true nature of reality. Einstein's equations of special and general relativity do not describe a universe where time flows. They describe a four-dimensional structure called space-time, where time is a dimension much like the three dimensions of space: length, width, height, and duration. In this picture, your life is not a sequence of moments happening one after another. Your life is a single four-dimensional shape called a world line, a curve through space-time that stretches from your birth to your death. Every event that has ever happened exists as a point in this four-dimensional structure. Every event that will ever happen exists as a point in this structure. The past has not vanished. The future is not empty. Everything simply is. The block universe is sometimes called eternalism because all times are equally real, equally present, equally existent. Consider a loaf of bread. You can slice it in different ways. Slice it straight across, and you get one pattern. Slice it at an angle, and you get a different pattern. Both slices are equally real cross-sections of the same loaf. In the block universe, moments are like slices of the four-dimensional loaf of space-time. Different observers, moving at different velocities, slice the loaf at different angles. They disagree about which events are simultaneous, but all the slices exist. All the moments are real. Your 5th birthday party is still happening somewhere in the block. The day you will die is already out there, fixed in the geometry of space-time. You are not moving through time in any objective sense. You are a static world, and your consciousness is experiencing different cross-sections of yourself, labeling each one as now. This interpretation is not speculation added on top of Einstein's physics. It is the most straightforward reading of what the equations describe. Time and space are unified into space-time. All points in space-time are equally real. The present moment has no special status. The flow of time is not a feature of the mathematics. But if this is true, the implications are staggering. If the future already exists, can you change it? If your decisions tomorrow are already out there in the block, fixed in space-time geometry, were they ever really decisions? The block universe seems to imply determinism, but not the familiar kind where the past causes the future. This is a deeper determinism where past, present, and future all simply exist timelessly, none causing the others, all equally frozen in the four-dimensional structure. Philosophers have debated this for decades. Some argue that the block universe is compatible with free will. Your choices are real. They are part of the block. The physical process of your brain deliberating, weighing options, and selecting an action is a genuine process that shapes your world line. It is just that this process, including its outcome, is part of the eternal structure. You still made the choice. The choice still matters. It is simply that the choice already exists from a timeless perspective. Others argue that this guts free will of any meaningful content. If your future actions are already fixed in space-time, then in what sense did you choose them? You might feel like you are deliberating, but the outcome was always going to be what it is. The sensation of choice would be real, but the openness of the future would be an illusion. Some physicists propose a modification called the growing block universe. In this view, the past exists, the present exists, but the future does not yet exist. The block grows as time passes, adding new slices of reality. This preserves some openness to the future, while maintaining the reality of the past. But it requires identifying a special universal present, which relativity seems to forbid. The honest answer is that physics does not settle this question. The equations of relativity describe a block, but equations describe structure, not metaphysics. Whether the block interpretation captures the true nature of reality or is merely a useful mathematical representation remains an open question. What is certain is that many working physicists take the block universe seriously. It eliminates the problem of time in quantum gravity. It explains why the laws of physics are time-symmetric. It makes sense of relativity's denial of universal simultaneity. The block is not a fringe idea. It is arguably the default interpretation among those who take relativity seriously as a description of reality. If the block universe is correct, then every moment of your existence, every joy and every sorrow, every triumph and every failure exists eternally in the geometry of space-time. Your death does not erase you. It is simply a boundary of your world line, beyond which the curve does not extend, but everything within that boundary remains. Your life is not something that passes and vanishes. It is something that exists timelessly as a permanent feature of the universe. Einstein found comfort in this idea when Beso died. Perhaps he found comfort in it facing his own death. The distinction between past, present, and future is only a stubbornly persistent illusion. Beso had not ceased to exist. Beso was still there in the block, still real, still part of the eternal structure. He had just departed a little ahead. The block universe explains the structure of time. It explains why relativity denies universal simultaneity. It explains why the laws of physics work equally well forward and backward. But it does not explain the most immediate fact of your existence. Right now, this moment feels real in a way that past and future moments do not. You are not experiencing your 5th birthday. You are not experiencing the moment of your death. You are experiencing this moment, reading these words, conscious and aware in what feels like an undeniable present. If all moments are equally real in the block, why does this one feel special? Why does now feel like now? This is the hard problem of temporal consciousness. It is not a problem that physics alone can solve. Consider what your brain actually does when it experiences time. Your nervous system contains multiple specialized systems for tracking temporal information. The cerebellum handles timing on the scale of milliseconds, coordinating the precise movements required to catch a ball or play a musical instrument. The basal ganglia handle interval timing, tracking durations of seconds to minutes, allowing you to estimate how long you have been waiting or when to expect a reward. The hippocampus encodes sequences of events, creating the episodic memories that give your life a narrative structure. None of these systems measure time the way a clock does. They construct temporal experience from patterns of neural activity. Your sense of how long something lasted is not a direct measurement. It is an inference based on how much information your brain encoded during the interval. Time flies when you are having fun, because enjoyable activities engage attention outward, reducing the density of memory formation. Less recorded means shorter perceived duration. Time drags when you are bored, because boredom turns attention inward, increasing awareness of each passing moment. More recorded means longer perceived duration. Fear slows time. When you experience a terrifying event, your amygdala kicks into overdrive, encoding details at a much higher rate than normal. Later, when you recall the event, the dense memory creates the impression that time passed slowly. But laboratory experiments show that perceptual processing does not actually speed up during fear. People in free fall do not see events in slow motion. They cannot read numbers flash too quickly to perceive under normal circumstances. The slow motion effect is a retrospective illusion created by memory density, not a real-time change in perception. Your experience of duration is a story your brain tells after the fact. The present moment is equally constructed. What philosophers call the specious present is the interval that feels like now, and research suggests it spans approximately 2 to 3 seconds. Events within this window feel simultaneous, unified, present. Events outside it fall into the categories of remembered past or anticipated future. The boundaries are not sharp. They shift with attention, emotion, and context, but the window exists. The present is not an instant. It is a constructed duration. Within this window, your brain performs a remarkable feat of integration. Information arrives from different senses at different times. Vision takes about 80 milliseconds to process. Sound takes about 50 milliseconds. Touch takes about 20 milliseconds. If your brain presented each sense as it arrived, your experience would be fragmented and chaotic. Instead, your brain holds fast signals, waits for slow ones, and stitches everything together into a unified present moment. This is temporal binding. It creates the seamless now you experience. But that now is a construction, a useful fiction, a post-processed edit of raw sensory data assembled into something your consciousness can work with. Patients with specific types of brain damage lose the normal experience of temporal flow. Some describe the world as a series of disconnected snapshots with no sense of continuity between them. Others lose the ability to distinguish past from present, experiencing memories as if they were happening now. Still others lose the sense that time is passing at all, trapped in an eternal present with no feeling of duration. These cases reveal that temporal experience is not a passive perception of an external reality. It is an active construction that healthy brains perform automatically. Damage the right circuits and the construction fails. The experience of time flowing is a feature of brain function, not a feature of the universe. This does not tell us whether time really flows. It tells us that our experience of time flowing is generated inside our heads. The feeling of now is a neural creation. The sense of moments passing is a product of information processing. Whether these experiences reflect something true about external reality or are entirely internal constructions remains unknown. Some theories propose that consciousness experiences time because it can only process a limited slice of information at once. The spotlight of attention moves through representations stored in memory and prediction systems. The sequential access creates the experience of flow. In this view, the block universe could be entirely real, and our experience of moving through it would be a consequence of cognitive limitations rather than evidence against the block. Consider reading a book with a flashlight in a dark room. The flashlight illuminates only one page at a time. Your experience of moving through the story is created by the flashlight's movement, not by the book changing. Consciousness might be the flashlight. The block universe might be the book. The experience of time passing would be real for you without requiring time to pass in any objective physical sense. This raises questions that physics cannot answer. What is it about certain physical systems, specifically brains, that generates the experience of temporal flow? Could other physical systems have similar experiences? Is there something special about the way consciousness relates to time? Or is our experience simply one more emergent illusion arising from underlying physics that knows nothing of flow? These questions touch on the deepest mysteries in philosophy of mind. They may not have scientific answers. They may represent the boundary where physics hands off to metaphysics, where equations end and speculation begins. What we can say is that your experience of time is not a transparent window onto reality. It is a construction shaped by evolution to help you survive, implemented by neural circuits that can malfunction or be altered, and potentially disconnected from the true nature of time itself. The now that feels so real, so immediate, so undeniable, is a product of your brain, and your brain evolved on the African savanna to track predators and find food, not to accurately represent the four-dimensional geometry of space-time. Every science fiction story about time travel gets it wrong, not because the writers lack imagination, but because the reality is stranger than fiction can capture. The question is not whether time travel is possible. Time travel is already happening. You are doing it right now. The real question is whether you can control it. Forward time travel is not speculative. It is not hypothetical. It is measured fact. Every astronaut who has ever orbited Earth is a time traveler. At orbital velocities, roughly 28,000 kilometers per hour, time dilation causes clocks to tick slightly slower than clocks on the surface. Astronaut Sergei Krikalev spent 803 days in orbit over his career. When he returned to Earth for the final time, he had aged approximately 0.02 seconds less than people who stayed on the ground. He traveled 0.02 seconds into Earth's future. The effect is tiny, but it is real. It is measured. It is time travel. The International Space Station moves fast enough that astronauts age about 0.01 seconds less per year than ground-based humans. After 6 months in orbit, a crew member returns, having skipped roughly 0.005 seconds into Earth's future. They are now living in a moment that Earth reached slightly before they did. This is not metaphor. This is the same physics that makes GPS satellites work. Scale up the velocity, and the effects become dramatic. At 90% of light speed, time passes at 44% of the normal rate. Travel for 10 years at this speed, and 23 years pass on Earth. You have jumped 13 years into the future. At 99% of light speed, time passes at just 14% of the normal rate. 1 year of your time equals 7 years back home. At 99.9999% of light speed, the ratio becomes extreme. 1 year of travel corresponds to 707 years on Earth. You could leave today and arrive in the year 2732, having aged only 12 months. The energy requirements are staggering. Accelerating a single kilogram to 99% of light speed requires energy equivalent to roughly 10 megatons of TNT. Accelerating a spacecraft with human occupants would require energy production beyond anything our civilization can currently achieve. But the physics permits it. The equations allow it. The only barriers are engineering and energy. Given sufficient resources, you could attend the funeral of everyone you have ever known while aging only a few years yourself. This is the twin paradox made real. One twin stays home. The other travels at relativistic speeds. When the traveler returns, they are younger than their sibling, decades younger, centuries younger. Depending on the velocity and duration, the traveling twin has jumped into the future. They cannot go back. Forward time travel is permitted by physics. It is merely expensive. Backward time travel is different. Traveling into the past means arriving before you left. It means effects preceding causes. It means the possibility of paradoxes so severe that logic itself seems to break. The grandfather paradox is the famous example. You travel back in time and prevent your grandfather from meeting your grandmother. Your parent is never born. You are never born. But if you were never born, you could not have traveled back to prevent the meeting. So your grandfather does meet your grandmother. So you are born. So you travel back. The loop has no consistent resolution. Physicists have proposed several solutions. The Novikov self-consistency principle suggests that the laws of physics conspire to prevent paradoxes. If you travel back in time intending to kill your grandfather, something will stop you. Your gun will jam. You will miss. You will have a change of heart. You might even discover that your attempt to kill him was always part of history. That your grandfather survived precisely because of your intervention. The universe protects its own consistency. Paradoxes are not prevented by fiat. They are prevented by physics. The many worlds interpretation offers a different solution. When you travel back in time, you do not enter your own past. You enter a parallel universe's past. Your actions create a branching timeline. In this new branch, your grandfather dies and you are never born, but your original timeline continues unchanged. You still exist because you came from that original branch. There is no paradox because you are not affecting your own history. You are creating new history in a different universe. Stephen Hawking proposed the chronology protection conjecture. He suspected that quantum effects would destroy any time machine before it could create a paradox. Wormholes might theoretically connect different points in time, but attempting to use one for backward time travel would cause quantum fluctuations to build up, generating infinite energy at the throat of the wormhole and destroying it. The universe censors backward time travel. The mechanism is not arbitrary. It emerges from the physics of quantum fields in curved spacetime. None of these proposals are proven, none are definitively ruled out. The mathematics of general relativity does permit solutions involving backward time travel. Closed time-like curves are paths through spacetime that loop back on themselves. Travel along such a curve and you return to your starting point in both space and time. You arrive before you left. Solutions containing closed time-like curves exist. Kurt Gödel found one in 1949, describing a rotating universe where such curves are possible. Rotating black holes described by the Kerr metric might contain them. Cosmic strings moving past each other at high speeds might create them. But none of these solutions describe our actual universe, Our universe does not rotate the way Gödel's does. We have never observed a traversable wormhole. Cosmic strings remain hypothetical. The mathematics permits backward time travel. Reality may not. The honest assessment is this: physics does not forbid backward time travel. It puts obstacles in the way that we may never overcome. The equations say, maybe. The engineering says, not yet. The philosophy says, paradoxes must be resolved somehow. Whether the resolution prevents backward time travel entirely or merely constrains it remains unknown. What we know for certain is that the future is accessible. Given enough energy, you can skip ahead. You can see what happens next. You cannot come back to tell anyone about it. The universe had a beginning. It will have an end. And when that end comes, time itself will lose all meaning. Roughly 13.8 billion years ago, the observable universe emerged from a hot, dense state of extraordinarily low entropy. Space expanded, matter cooled, particles combined into atoms. Atoms gathered into stars. Stars forged heavy elements and scattered them through space when they died. Planets formed. On at least one planet, chemistry became biology. Biology became consciousness. Consciousness began asking questions about time. The expansion continues. It is accelerating. Dark energy, a mysterious property of space itself, pushes the universe apart faster and faster. Current measurements suggest this acceleration will continue forever. The universe will not collapse back on itself. It will not cycle into a new Big Bang. It will expand eternally, cooling and diluting until nothing remains but empty space and fading radiation. This is the heat death of the universe. It is the most likely fate of all existence. The timeline stretches beyond human comprehension. Stars will continue forming for another 100 trillion years. That number is already beyond intuition. The universe is currently 13.8 billion years old. It will continue making stars for roughly 10,000 times longer than it has already existed. Then the raw material will run out. Gas clouds will be exhausted. The last stars will ignite, burn through their fuel, and die. After the last star dies, the universe enters the degenerate era. White dwarfs, neutron stars, and black holes remain. These objects cool slowly, radiating away their residual heat into the expanding void. White dwarfs take quadrillions of years to fade completely. The numbers become meaningless. 10 to the power of 15 years. 10 to the power of 20 years. Timescales so vast that the entire current age of the universe is a rounding error. Black holes persist longest. They do not last forever. Stephen Hawking discovered that black holes emit radiation through quantum effects near their event horizons. This Hawking radiation carries away energy. The black hole slowly evaporates. A stellar mass black hole takes roughly 10 to the power of 67 years to evaporate. A supermassive black hole like the one at the center of the Milky Way takes roughly 10 to the power of 100 years. That is a 1 followed by 100 zeros. There is no meaningful way to conceptualize such a duration. Eventually, the last black hole evaporates. The universe contains nothing but scattered particles, cooling photons, and empty space stretching in every direction. Entropy reaches its maximum. No further change is possible. Every region of space is identical to every other region. Every moment is identical to every other moment. This is where time ends. Not because something destroys it, because time requires change to have meaning. Time is not a background against which events happen. Time is the measure of change. It is the dimension along which entropy increases, along which causes precede effects, along which memory accumulates and anticipation projects. Without change, these concepts dissolve. If nothing can happen, if no process can unfold, if every moment is identical to every other moment, then calling them different moments becomes meaningless. The universe does not end in fire or ice. It ends in sameness. It ends in the inability of anything to ever happen again. Some physicists speculate about alternatives. Perhaps dark energy will strengthen over time, accelerating expansion until it tears apart galaxies, then stars, then planets, then atoms themselves. This is the Big Rip. Time would not end gently. Everything would end violently, shredded by the accelerating expansion of space. Current evidence does not favor this scenario, but it is not ruled out. Perhaps dark energy will weaken or reverse. Gravity might eventually overcome the expansion, pulling everything back together in a big crunch. The universe would collapse to a singularity, possibly followed by another Big Bang, another expansion, another cycle. Time might be infinite, but cyclical, an eternal return with no ultimate end. This scenario requires dark energy to behave in ways we have not observed. It remains speculative. The most likely fate is heat death, the slow fade, the eternal nothing, the end of time through the exhaustion of possibility. But knowing the end does not diminish the middle. You exist in a universe where time still flows, where change still happens, where entropy has not yet reached its maximum. You exist in the brief window between the low-entropy birth and the high-entropy death of the cosmos. This window spans trillions of years, but it is finite, and you are here, conscious, aware, experiencing moments that will never come again. If the block universe is correct, your existence does not vanish when you die. Every moment of your life remains real, frozen in the geometry of space-time, as permanent as the block itself. Your death is a boundary, not an erasure. Everything you have ever experienced continues to exist in the eternal structure. Einstein found comfort in this when he faced his own death. Perhaps there is comfort in it for you. If time truly flows, if the future is genuinely open, then every moment matters precisely because it passes. The impermanence is not a tragedy. It is what makes choice meaningful. It is what makes action consequential. It is what makes love precious. Things that last forever have no urgency. Things that pass require attention now. Either way, one truth remains: you are a pattern of matter that has become aware of itself. You are atoms arranged in a configuration that can contemplate its own existence in time. You are the universe experiencing itself, asking questions about its own nature, wondering about the dimension that carries you from birth to death. That is extraordinary. That is worth marveling at. That is worth remembering. For 13.8 billion years, the universe evolved in darkness, unwitnessed, unknown to itself. Then, on a small rocky planet, orbiting an ordinary star in an unremarkable galaxy, matter learned to ask, what is time? The question is not yet answered. Maybe it never will be. But the asking itself, the fact that the cosmos can reflect on its own temporal nature, might be the most remarkable thing time has ever produced. You are time thinking about itself. You are the universe wondering about its own dimension. You are a brief arrangement of matter that has somehow become aware of the flow that carries all things from beginning to end. And that is not nothing. That is everything.